Okay, so the next talk is Vaclav Zatloukal, who's talking about shape gauges and rotating blades, new variables for fundamental interactions.
Okay, thank you. So I will talk about shape operator and a certain generalization thereof, with a vision to treat general gauge theories and fundamental interactions of physics. So let me try how this works. Yeah. So to motivate a little bit, this is the standard model of fundamental interactions, particle interactions, and it's a sizable. It's the Lagrangian standard model. It's a sizable expression in itself. It features various kinds of fields, but actually, if you write things out, really, you get this expression. So this is the beautiful model of particle physics that we have nowadays. And one thing that there might be a way to organize the particles interactions in some more transparent way. So this is really the driving force behind, or the idea behind what I'm going to talk about, the motivation for my work. And as I said, so there are various kinds of fields laying on the space-time. So scalar valued fields, spinor valued fields that describe matter. Then the mediators of interactions, which are the connections, or the gauge fields. And so these gauge fields are those that I will focus on during the presentation. And these enter the Lagrangian via so-called covariant derivatives. And if you take a commutator of these covariant derivatives, you get the field strength, for instance, the electric and magnetic fields. And the expression before was missing the gravity part of fundamental interactions. It's also fundamental interactions. So we would have, again, some other types of fields, like metric or tetrahedral vectors or connection vectors. So I would like to phrase everything in terms of geometric algebra. Indeed, there is a nice correspondences between a traditional way of writing things on the right with matrices and let's say 4-component Dirac spinors. On the left, there is the geometric algebra equivalent of those, and but I will really focus only on the gauge fields, on the connections, this aiming part of the method. But yet, I believe that since one wants to provide a simpler, unified model of physics, it is a good idea to do it with a unified mathematical framework, of course, which is provided by geometric algebra, where all those various kinds of fields eventually live in a common space, geometric algebra. So the outline goes as follows. I will recall some major facts about embedded manifolds, introduce the shape tensor, and then go on to generalize these ideas, take the crucial ideas to the setting of a general vector bundle over a manifold. So this is the setup for generic gauge theories like electromagnetism or electroweak theories. And then we'll show what the shape operator in that setup would correspond to and how this could be useful to do physics, to do calculations, solve equations. So the idea behind this is the quote from David Estenesh: the treatment of intrinsic geometry can be simplified by coordinating it with extrinsic geometry. And I would like to argue this applies not only to manifolds, to surfaces, or embedded manifolds, but also to bundles of gauge theories. So let's see how we go. So this is the slide with the embedded manifold. So indeed, we have some ambient space, capital N dimensional big space. There is a surface embedded manifold of dimension d, let's say, and at each point of this manifold, we have the tangent plane. These tangent planes can be very neatly characterized by unit d blades. This IM, those are referred to as pseudoscalars of the manifold, pseudoscalar field of the manifold. And so it's a function that changes along the manifold. And if we want to see how the manifold bends, how the tangent planes how they rotate as we move along the manifold, we take this we take a derivative. So mu just enumerates the directions in the coordinate space of the usual coordinates. We divide out also the IM for convenience, and this is called the shape operator. And there are some standard references, H plus S and D plus L, with the notation of the morning sessions, which give details about this. And so, and the covariant derivative from an embedded manifold is usually introduced as by taking a tangent vector, differentiating it partially, and then projecting it onto the manifold so that it remains tangent. This is the classical differential geometry. It turns out that this is equal to an expression here. So where there is really this minus S mu plays the role of the gauge field or connection coefficients. Yeah, so it's partial derivative part and then some correction part which rotates the vector a little bit. A nice thing about this expression 3 is that it can be immediately generalized to covariantly differentiate generic multi-vector valued fields. Yeah. And what about the curvature? So the curvature, it's given by the commutator of covariant derivatives, but since this connection coefficients S mu are now given by the rotating blade pseudoscalar, in fact, we get a simple expression for the curvature which features only the commutator of these shape operators. Since the shape operators themselves have kind of a potential rotating blade. And one can compare this expression with, say, the expression for intrinsic Riemann tensor in terms of the Christoffel symbols, where we have also the derivatives of the Christoffel symbols. Yeah. Okay, so with those lessons, we would like to consider generic vector bundles, because this is where the gauge theories are mathematically treated. So let's take a d-dimensional manifold within space-time, so just an abstract set of points, and consider a little n-dimensional internal space. So for instance, for electromagnetism, we would have little m equals 2, because it's a two-dimensional real space, and there is one bivector, and we can make one type of rotations within this space. And with this structure, we can introduce electromagnetic connection and do electromagnetism. Essentially, this one bivector is what people would usually denote by imaginary I in for instance, quantum electrodynamics. Anyways, but on top of this, we'll think of this internal space as embedded in some bigger space of dimension capital N, in some bigger like ambient kind of space. So this is really analogous to the embedded manifold picture. Yeah. So the little n-dimensional space would be tangent space in the embedded picture. And the ambient space is higher dimension. Okay. So and in this big N space, of course, we consider geometric algebra over this E capital N. So we take a Euclidean n-dimensional space, just Euclidean metric for simplicity and definiteness. And there the covariant derivatives in general on those vector bundles, they have this form of equation 6. So there are some connection by vectors, v mu. And yeah, this is a generic form for metric compatible covariant derivatives on the vector bundle. So I mean, I will just state some facts for the big bundle in general. So the important notion is the one of H transformations. So these are local rotations in those big vector spaces, in those fibers E capital N. And one postulates that they should commute with the covariant derivative. Yeah, I mean, so this U is the rotor. Of course, I don't have to maybe stress this at this place. So everybody knows that doing rotations is much more efficient with the rotors, with sandwiching using rotors. Okay, and so from this requirement of commutation between the H transformation and the covariant derivative, we get this right-hand side of 7. So this is the transformation rule for the connection. And so the connection coefficients transform in this funny way. And yeah, in general, the curvature is given by formula 8. So if we don't assume anything about the connection coefficients, we will have this general formula. Again, it comes from the commutator of covariant derivatives. Okay, time flies. So now we'll think about this scenario. So let's take the big space, the ambient bundle with a flat connection. So we have just partial derivative and no connection coefficients. And now let's choose distribution of little n dimensional blades inside this bigger space, and let's call them capital Tx. So it's kind of, I mean, it's analogous to the pseudoscale of the manifold, and the letter is also a bit analogous, but not to say, maybe just to distinguish things. But the Tx is really the rotating plane. And okay, and so we can have vectors which are living inside the plane, vector fields that are parallel to the planes T of x at every point. And we can project the flat connection onto this subbundle defined by the Lagrange blades. And a little calculation shows that, okay, this is the equation 9, that indeed, if we take the partial derivative, so that's the covariant derivative in the big space, in the flat space, we project it, and again, it can be given by this formula using S mu, where S mu is defined in complete analogy with the shape operator of embedded manifolds. So it's a differential of this rotating blade. Being a differential, it satisfies this equation 10, and hence the curvature. So S mu are the connection coefficients, but they are special. So the curvature corresponding to these is given by 11. So we can choose either to use the algebraic decomposition into shape operators, or a differential expression which is linear in S. Each of them might be useful. And now what does this have to do with our treatment, with the usual treatment of gauge theorems? So first we know that, there are many ways how to approach this problem, but let me try to take this one. So we have this rotating blade. We defined the covariant derivative on the subbundle, and the rotating blade satisfies equation 12. So it's parallel transport, so to say. with respect to this covariant derivative that it had defined in the first place. Okay, so, and now if we write this rotating blade as some rotation u, now I'm using again the same letter, but yeah. Okay, it's a rotating blade, so it can be written as a rotation of some reference constant blade T0. And if we sandwich the equation 12 to get 13, we find out that this expression here, which is gauge transformation of the minus S mu, I recall that the gauge transformations were given here by in equation 7, this notation with the bracket in the superscript. Those are bivectors that are either parallel to T0 or completely transverse to T0. And let's focus on the parallel part. So it defines some connection within this constant subspace, and let me call this standard connection. So this would be the AMU standard connection, for instance, the electromagnetic connection, right? If the little n is equal to 2, yeah. So we envisage the T0 to be two-dimensional. We can rotate there. We can define a connection. But here we are working in a bigger space where this two-dimensional surface, two-dimensional plane is embedded. But we got to this standard gauge. We will see some explicit example of plane electromagnetic wave. So we will have the A mu at the beginning, and we will see how this S mu looks for the electromagnetic wave. So these two, A mu and the minus S mu, are gauge related. So they are different gauges for the same connection, in fact. So one could think like we start from the standard connection, we inflate the number of dimensions, and then suddenly we can make more general gauge transformations, and we might be lucky enough to make a gauge transformation that leads us to a shape gauge. Again, shape gauge defined basically by this equation 10. This is the characteristic equation for the shape gauge, something that the gauges don't, the connections don't satisfy in general, but the shape gauges. Okay, I don't know, maybe not much time, but the interesting thing about this this way of approaching is that at the capital T there is some ambiguity, of course, how to choose the rotor U that translates between the constant plane T0 and this rotating blade T. So we can make for any rotor U that does this, we can have also some U0 part which rotates only within the T0 plane, and the result would be the same. And if we take this product to make our gauge transformation from the shape gauge to the standard gauge, what we get is another standard gauge. So this is gauge related to the standard gauge by standard gauge transformation U0. I mean, there is a lot of standard and gauge words in the talk, but I'm trying to maybe present more than I can. Anyway, but the moral is that in some sense from this, from the certain T of X function for a certain distribution of this rotating planes, we get all the standard, we get the whole standard gauge orbit. So this gauge redundancy, which is inherent in the standard description of gauge theories, is kind of swallows to one point where this or one function T of X, or there might be several, but the whole orbit comes to this one rotating blade. Yeah, I can go on. This is going to be the last slide. So what this could be helpful for. So indeed, this is basically from the point of view of starting with the standard gauge, we inflate the number of dimensions and we have more gauge freedom, and we can rotate the shape gauge, which satisfies some nice properties as regards the curvature, because the curvature is in nice terms. And so, for instance, if we take the Young's equations, so it's like a generalization of Maxwell's equations, but this can also be, this can also be reduced to Maxwell's equations, for instance. So equation 16, where we have a covariant derivative on the field strength, so on the curvatures. We can envisage changing the gauge, rotating from this A mu standard gauge to a shape gauge in which the equations would acquire a nicer form, because we have the form 17, where the curvature is given by the commutator of the shape operators. So it might look like some maybe simplification, or maybe at least reformulation of the problem. And of course, there is also this condition on the shape gauge being the shape gauge. But if we take the ansatz in this form, the second equation in 17 is automatically satisfied, and then basically we have an equation for this rotating blade, which is second order nonlinear, but it has some structure, and it's an equation for for a function which is n blade valued, but it has no space-time indices anymore. So it's last comment, looking at the first equation in 17, it would be interesting to have simpler, like more primitive equation for the S mu itself, and something of the sort in the brackets, because this 17 looks like it's complicated. I mean, there are two shape operators, and then maybe the fundamental equations for physics should look somehow simpler, but who knows? An equation, so one would like to have an equation from which those standard ones would follow, for instance, in some sense. Okay, so this is the conclusion, and so I try to argue that in fundamental physics it might be useful to work in the shape gauge rather than standard gauges. Although one has to like put some extra dimensions in and stuff, but some other things simplify. The question about existence of shape gauges for any given standard gauge is kind of what we are working on to nail it down like rigorously. But this is an analogous question to like, embedding of Riemann in manifold. So this is somehow a generalized, more general question for embedding vector bundles inside bigger vector bundles. And indeed, so there is this rotating blade variable would be considered as really fundamental variable for physics, because this is what things eventually boil down to. It would be nice to have some direct physical interpretation of this capital T if there is one. So there is an interpretation in the sense that you take T differentiated, get the shape operator, then take the commutator, and you have the curvature, which is the field strength. But this is not what I would say direct at this moment, but something that really one sees physically what happens when physical objects are moving, like how this T is describing it. This is all. And yeah, in the next talk we will see some more information.
Okay, thank you. We have some questions. Please.
Vaclav, thank you for the presentation. Now, I'm glad to see the standard model being addressed directly as you're doing. My question is, when you introduced, before you introduced the capital T subbundle, The approach to me looked in the first few of your graphs just like the usual standard model approach to gauge theory with matrices. What role did geometric algebra play in that, in your starting slides?
I would say the geometric algebra plays purely practical form at the moment. It's just much easier to use rotors to do the gauge transformations. Also, we need to rotate the blades, which would be very tedious with matrices. And I mean, it doesn't have, at the moment, we don't have like some unification of fields within the geometric algebra. We are just dealing essentially with gauge fields, which are bivectors, so one could just represent them with antisymmetric matrices. But I just find it more convenient to use the formalism of geometric algebra, really nothing deep at the moment.
Okay, thank you.
Yeah, but there's just one question: what happens when all this is quantized? Because the standard model is a quantum field theory, or are many quantum field theories. Yeah. Then you introduce the Higgs, then the symmetry becomes broken, and all that. Is this special gauge then? Okay, let's be more precise. This special gauge will influence the process of quantization of the Young-Mills field. Certainly. Is that an advantage, or it cannot be seen yet? Okay, that's something for the future to be seen, if it is an advantage to use such a gauge, and then the symmetry will be broken. And this should also be considered. Maybe you arrive at different answers in this way than the usual interpretation of when the Higgs model is introduced into this, and when all the fermionic source fields are coupled to the Young-Mills, that is here only a free Young-Mills field.
Yeah, I mean, so we are not dealing with the quantum field theory. This was for the motivation, but we are more thinking about classical electrodynamics, gravity, and how this can be used there. But it's true, like it gives you a different structures, different variables for a Lagrangian. And for instance, if you recall this Fadejev-Popov procedure for dealing with the gauge freedom in non-abelian or even abelian gauge theories, then it's kind of bothering all this gauge freedom in the standard gauge. And since we are swallowing the whole gauge orbit, this might be of some importance in the path integral approach.
We're running short of time. Can we check if there's online questions? No online. Did you have a question, Martin?
Yeah, just in relation to what you said. Since you brought up the Fadejev-Popov procedure, but can you elaborate on that? So do you think this will reduce the gauge degrees of freedom that you have to fix there in a Fadejev-Popov procedure, or what's the relation
to
there?
Me, it seems that it might, using this variable t, the rotating blade, you don't see the gauge freedom, or you really don't have this standard gauge freedom within the standard gauge orbit. And well, of course, you have to like rebuild a lot of other things, but yeah, then there would be not this redundancy in the path integral that you have to deal with using the ghosts. And there might be some other redundancy, but that remains to be seen.
Okay, thank you.
Thank you. Okay, thanks for